is a transistor, and the schematic symbol for it over here is this diagram here. And you can see, just to kind of orient, there's the three leads on the transistor, and those correspond to the three things here. So we've got an emitter, a base, and a collector. And just to kind of orient ourselves, this would be the emitter, the middle lead is the base, and this lead is the collector. So that's just kind of how this corresponds to the schematic symbol for it. And what a transistor is it's basically a current switch. What that means is that if we establish a current from the base to the emitter in this direction, that'll switch the transistor on, and the transistor will allow a much larger current to flow from the collector to the emitter. So what we can do with that is something like this, which is this circuit that we've got set up over here. And basically what this circuit does is we've got a switch that allows us to complete a circuit that allows current to flow, like I said, from the base to the emitter. From the base to the emitter. So if we close this little switch, push this button, that establishes a circuit like this and causes current to flow from the base to the emitter. That turns the transistor on. Once the transistor is turned on, then current is then allowed to flow from the collector to the emitter in this direction, and that allows this sort of second part of the circuit to work, where current will then flow from the battery here through this resistor, through this light-emitting diode, or LED, which will turn that on, and we'll see this light up, and then through the transistor. And then if we aren't putting current from the base to the emitter, then the transistor shuts off, and so this other part of the circuit will shut off, and the LED will shut off. So we can see in the circuit, the first part of the circuit, we've got a positive voltage rail here. We've got this resistor that goes through the button, and then into the base of the transistor. And then that will allow us to get that first current flowing to turn the transistor on, and then that'll go back out through the negative terminal here. And once the transistor's on, that'll allow current to flow from the positive rail here, through the resistor, through the LED, into the transistor, through the transistor, now that it's on, and then out through this, this negative rail. So if we push the button, transistor turns on, and consequently the LED turns on. Okay, so far so good. Let's take a look at another circuit, which is on the other half of this breadboard here. And in this circuit, we've got something a little bit different going on. We've got the transistor is off, but with the transistor being off, we have this part of the circuit here, which actually allows current to flow through this resistor and then through the LED. So the LED is actually already on, which you can see right here. So the LED is on right now, but if we turn the transistor on, then we'll actually sort of allow current to flow through the transistor here, and that'll lower the voltage potential at this node. And so instead of having a positive voltage here that allows current to flow through the LED, we won't have a voltage differential between the two parts of the transistor when the transistor is on. And so that'll actually have the effect of turning the LED off. So if we do that, we see the LED turns off. So in this case, we're using this transistor as a switch to kind of invert the voltage here. So if we look at the voltage here, right now it's 0 volts because this switch is open, and the LED is seeing a positive voltage. And then if we turn the switch on, we have a positive voltage here, but then we get 0 volts differential here across the LED, and the LED turns off. And so this little circuit is called an inverter. And there's actually a symbol for it, and that's this little triangle with a circle. And there's a sort of a truth table for the logic. It's pretty simple. If the input is off, the output is on, or if the input's a 0, we kind of use that as to represent off. The output is on. If the input is on, then the output is off. Pretty straightforward. So let's look at some other logic circuits that we can make with transistors. Okay, this next circuit that we'll look at, we've got 2 transistors. It's just kind of this left half of the board here. We've got 2 transistors, and the way it works is we've got these inputs, which again are kind of, I haven't drawn the whole circuit out, but we still have this resistor coming from the positive rail here through the push button switch and then into the base of the transistor. And so that allows us to put a current through that transistor. And we've got 2 of those. And so what happens is that if both transistors are turned on, then that will complete the circuit through this resistor here, and then through this LED, and then through the first transistor, and then over here and through the second transistor. And so if both transistors are turned on, then the LED will turn on. And this is a little piece of logic that is called an AND gate. And this is the truth table for it. This is the symbol that we would use if we were drawing a more complex logic circuit. We would actually, instead of drawing all the little transistors, we would just kind of draw this whole circuit as just an AND gate using this symbol. It's kind of rounded on this side and squared off on this side. And the truth table for it says that if A and B are off, then the output is off, and that's kind of what we have now. So both of these are off. I'm not pushing either one, and the output is off. If B is on and A is off, then the output is also off, and we can test that just by pushing the button, and the LED doesn't come on. Same thing, if A is off, if A is on and B is off, then the output is also off. We can test that by pushing the button here. But if both of them are on, then the output is on, and that makes sense. If both of these are on, then that completes the circuit all the way through. And so if I push both the buttons, then you can see the LED comes on because we're completing the circuit all the way through. So how about this other circuit over here? It's a little bit different. I'll show you the circuit diagram first. And the circuit diagram for this is a little bit different. So we still have two transistors, we still have our LED, but they're wired up just a little bit different. So in this case, the transistors are kind of in parallel. And so if either of the transistors is on, then the LED would come on, because we can complete the circuit through this transistor or through this transistor. So if we look at the circuit kind of closely here, we can see that from the positive rail, we come through this resistor and then through the LED, and then we can go through this first transistor. So from the the collector here to the emitter, or we can actually kind of come over to this transistor through the collector and out through the emitter. And then so if either of these transistors is on, then the LED will be on. So we can test that out. So if we turn this one on, it comes on. If we turn this one on, it comes on as well. And so this is something called an OR gate, which makes sense. If this is on, then the output is on. And so this is the truth table for it. So if both are off, the output is off, which is what we see here. But if one of them is on, then the output's on. If the other one is on, the output's also on. And also if both of them are on, because then that'll just complete the circuit either way. And of course, either way, current will flow, and so it'll be on. So we push both buttons, you can see it's on. So either way, or both, it doesn't matter. It'll turn on. So you can see here we've got two different circuits. They're very similar, but slightly different operation. One is an AND operation, the other is an OR operation. So let's take a look at something a little bit more complicated. So this is a different board here, different circuit, and let me just power this up. So this we've got actually 5 transistors in this circuit, and it is basically the same kind of idea here. We've got 2 inputs that we can, in this case, turn on and off with these little push-button switches, and we have got an output over here, which is this LED. And what we've built is what's called an exclusive OR gate, or an XOR gate, and it's similar to the OR gate, which is it's off if both A and B are off, and it's on if A or B is on. But what's different is that it's off if A and B are on. And so we can actually kind of see that operation. So right now it's off because neither of them are on. But if we turn on A, the output is on. And if we turn on B, then the output is on. But if we turn on both at the same time, the output goes off. And to kind of understand how that works, I've got the circuit diagram for what's built here. And you can see that if we just look at this part over here, it looks a lot like the OR gate, because we've got the 5-volt source going through a resistor through the LED, and that's what's going on here. So we have a 5-volt source going through the resistor, through the LED, and into either of these transistors. So it can go through either of these transistors. And then the inputs for those transistors are the A and B. So these yellow wires come over here and then jump over to the switches. So if either this or this is on, then that'll complete the circuit at least through to this point. And so in the OR gate, we just had this connected directly to ground. And so if this or this were on, then that would complete the circuit all the way to ground. But in this case, in order to get to ground, we've got to turn this transistor on too. Otherwise, we've got a 5 volts sort of connected back to 5 volts, and there's no voltage potential difference between 5 and 5, so the LED is off. So in order for this OR gate to work, essentially, this transistor has to be on. And that transistor is actually normally on, right? Because we've got this connected right to 5 volts. So we've got current flowing, from the base to the emitter. So this will normally be on, unless A and B are on. If A and B are on, then this node here is then going to be connected to ground. That'll turn off this transistor. So if A and B are on, then this transistor is turned off. And if this transistor is turned off, then this OR gate essentially doesn't work, which is kind of what we want to do, right? If A and B are on, we don't want to really do the same thing as the OR gate. We just want the output to be off. So that is essentially what's going on here, and so that allows us to build, it takes us 5 transistors to do it, but it lets us build this other logic element, which is this XOR gate. So again, we can see it work. If we have A on, it comes on. If we have B on, it comes on. But if we do both at the same time, it's not on. And of course, if they're both off, then the output is off as well. And so these are just a couple of the different gates that you can build with transistors, and here's actually kind of a whole list of different ones. So we saw, the AND gate, the OR gate, we just saw the XOR gate, and we're, of course, looking at the inverter here. There's also, you can make a buffer. I guess this is actually kind of the first thing we made with the transistor, which is the input was on, then the output was on, the input was off, the output was off. Not very exciting, but it can be useful. And there's a couple others that we could also make that we didn't look at, which are the not and, or NAND, the not or, and the not XOR, or the XNOR it's called. And these are basically the same as the AND gate, but the output is inverted. And if you look at the symbol, you have this little bubble on the output there, which just means that the output is inverted. And so it's basically the exact opposite. The XNOR is the opposite of the XOR, the NOR is the opposite of the OR, and so on. So you can build any of these with a few transistors, and then of course you can take these logic gates and then build more complex circuits that allow you to do arithmetic or store values in a memory and other things that allow you to build a computer.
Server latch.